You know, when you hear the word steel, you probably think of strength, right? Skyscrapers, legendary swords. And at the very heart of that strength is a transformation called Martensite. But what if I told you this process, born in the heat of a forge, holds secrets that stretch from the depths of space all the way to microscopic assassins? Let's dive in and uncover the real science behind it.
I mean, seriously. The very same physical phenomenon that gives a katana its legendary edge is also used by some of nature's tiniest predators to infect their prey. How is that even possible? Well, to get our heads around that, we first have to start with what we think we know about it.
Yeah, for centuries, martensite and steel have been basically the same word. It's that magic ingredient, the hard stuff that makes steel, well, steel. It's the result of that violent, rapid cooling process that blacksmiths have perfected over generations.
So, if I say Martensite or quench steel, what pops into your head? I'm guessing words like hard, brittle, and fast. And of course, you're probably picturing exactly this, a glowing hot blade getting plunged into water with a big hiss. Most of us would probably come up with a list that looks something like this. It's incredibly hard, it forms when you cool metal down really, really fast, and it's some special structure that you only find in steel. And look, these are the textbook definitions, but it turns out a lot of this common knowledge is either incomplete or just plain wrong.
So, let's start with the biggest misconception of all, that this is just a story about steel. Sure, it's absolutely critical for steel, but martensite is a way more universal phenomenon than most people realize.
And what's really fascinating here is the sheer range. I mean, look at this. We see this transformation happening in zirconia at a blistering 1200 Kelvin. But it also happens in solid argon-nitrogen mixtures near absolute zero at just 4 Kelvin. It's in shape memory alloys like copper aluminum, and even in certain polymers. This isn't just some quirk of steel. It's a fundamental process baked into the rules of materials science. And this just perfectly illustrates how widespread it is. Get this. Some viruses have a crystalline structure that acts like a tiny tube. When it's time to infect a bacterium, that tube undergoes a Martensitic transformation. It snaps from being long and thin to short and fat. And that physical change literally punches through the cell wall like a hypodermic needle to inject its DNA. I mean, that is just mind-blowing, right? Okay, so if it's not just for steel, what about its famous hardness? I mean, surely that part is true. Well, not exactly. The idea that martensite itself is inherently super hard is another major misconception.
So here's the crucial detail. The hardness in steel comes from tiny carbon atoms getting trapped inside the martensite crystal structure. They basically act like little wedges, distorting the whole lattice and making it incredibly difficult for the atomic layers to slide past each other. So let's be clear, martensite itself isn't what's hard. Think of it as the cage. The real source of the hardness is what gets trapped inside that cage, the carbon.
Okay, so we've cleared that up. So what is a martensitic transformation really? If it's not defined by steel or even by hardness, what is its true nature? Well, the answer lies in this beautiful, coordinated dance happening at the atomic level. It's what scientists call a displacive transformation. Now, unlike other transformations where atoms just kind of randomly break their bonds and rearrange themselves, here they all move together. Think of it like the difference between a panicked crowd scattering and a disciplined army marching in perfect formation. Every atom knows exactly where to go. It's this incredibly coordinated military-like shift from one crystal pattern to another. So let's just break this down. First, you've got the original crystal structure. In steel, that's called austenite. Now, when the temperature drops super fast, something incredible happens. Instead of atoms just wandering off on their own, that's a process called diffusion. They all shift together in a coordinated snap. This instant shift creates the new martensite crystal. And because every single atom moved in formation, the material itself visibly changes shape. And here's the proof that atoms aren't just wandering around. The interface of this transformation, the wave of change, can travel at speeds of up to 1,000 meters per second. That's about a fifth of the space shuttle's re-entry speed. It is so ridiculously fast that there's absolutely no time for atoms to diffuse. They have no choice but to shift together in this incredible atomic wave. So, what we have is a lightning-fast, coordinated atomic shift that's found in everything from steel to viruses. And we've been using it for literally thousands of years. You'd think we'd have it all figured out by now, right? But that's where this whole story gets even more interesting. Martensite is still full of these deep, unsolved puzzles. Yeah, the scientists who study this stuff are still stumped by some pretty basic questions. For instance, the interface between the old crystal and the new one. It doesn't form on a simple, neat geometric plane. It forms on what's called an irrational plane, this weird, complex angle that just defies any simple explanation. The alignment between the two crystals isn't perfect either. It's just a little bit off. And maybe the most puzzling thing of all is that when they calculate the shape change that should happen, it doesn't match what we actually see. It seems impossible, and yet it happens every single day.
And that really leaves us with this final, fascinating thought. This transformation is one of the most technologically important things on the planet. It's the backbone of our modern world. And yet, at its very heart, it's still a profound mystery. It's just a perfect reminder that even in the things we think we understand the best, there are always deeper secrets just waiting to be discovered.